and that'll be at 7 o'clock. And it will be in Milner 317. Now, I'll put all of this on the web, but that building is locked, so I will need to let you in. So if you would you come by 6:55 to the north side door. That's the one opposite Savisa. And I will let you in, and we'll start the exam at 7. So it'll be a 2-hour exam. I will give you plenty of time to do it. And the way this will work, there'll be 5 problems. Honours will do all 5, and everyone else will be judged on their best 4. So you can do all 5 problems if you wish. I'll just take the best 4 scores, or you can just hand in 4 as you choose. Now on Wednesday, I will discuss the practice test. I hope everyone's looking at. And so today, what I want to do is complete or prove proof of theorem 2.8. So let me state it again. Given a continuous function, f on any closed interval a to b, and an epsilon greater than 0, there exists a polynomial p of x so that the infinity norm of f minus p is less than epsilon. So you can get as close as you like to a continuous function uniformly on the interval using polynomial. So this is the Weierstrass approximation theorem. And last time I mapped out a strategy for doing this. And basically what we're going to do is start with a continuous function, approximate it by a piecewise linear function, and then approximate that piecewise linear function by a polynomial. So it's a 2-step procedure. Oh, and one other thing that occurs to me before I do that, on the web page you'll find correction to that example last time. So it does indeed work out. Okay, so let us fix f in the continuous functions on a to b and an epsilon greater than 0. Since it's a 2-step procedure, what we'll do is start with a piecewise linear function that comes within epsilon over 2, and then a polynomial that comes within epsilon over 2 of that. So choose a continuous piecewise linear function g so that f minus minus g infinity norm is less than epsilon over 2. Now, in order to approximate that piecewise linear function, we'll have to see that it can be written in a specific form. So, the next step is to show that any piecewise linear continuous function can be written as a sum of a linear function mx plus b and combinations of the following. Absolute values of x minus c, where c will be chosen. And the reason that this will work is, first of all, the linear function mx plus b, that's already a polynomial. But we saw last time that things of the form absolute value x minus c can all be approximated by polynomials. Okay, so we do this by induction on the number of changes of slope. Well, if there's no change in slope, then it is simply a linear function to begin with. So that's not a problem. So let's look at the case n equals 1. We have one change in slope, and so our piecewise linear function looks like this. Say. So there are only two slopes for the lines in the picture. One change over point. So how can we do this? So let us say that it changes at a point C. And let's give this function a name. This is h of x. And so we can write h of x in the following way. To the left of c, it has a certain slope. And I'll write it this way so that it's easy to match it up at the point C. m1 times x minus c plus b, and then m2 times x minus c plus b when x is less than or equal to c and when x is greater than or equal to c. So they match up with a common value of b at the changeover point. But we have two different slopes, m1 and m2. And so we want to write this as a linear term absolute value of x minus c. So alpha times x minus c. So we've got three things that we can choose. Let's write it in terms of x minus c. It's the same thing.
Are those two b's the same?
Yes.
The endpoint b and the that b?
That's a bad choice, isn't it? Let's make it d. Thank you. Whatever the value is at c, that's d. So I want to write it as a linear term plus some multiple of the absolute value of x minus c. Since I have three constants here that I can choose, m, k, and alpha, it should be possible to do this because I'm just matching two halves of the function. So to the left of c, h of x is this. So I want m times x minus c plus k. And now when x is to the left of c, x minus c is negative, so the absolute value is c minus x plus alpha times c minus x. And then to the right of c, I have this. So this is x less than c, x greater than c, and I have to match that with m1 x minus c plus d and m2 x minus c go the wrong way around, m2 and m1. No, I had it the right way around the first time. Okay, so m1, m2, and d are all given, and m, k, and alpha are free to choose. So let's try matching. So the slope of this linear piece is m minus alpha. So what we want is m minus alpha is equal to m1. That will match the slopes on the left of c. And I also want m plus alpha to be equal to m2. That will match the slopes to the right of c. Well, I can solve those equations if I add. These imply that m should be m1 plus m2 over 2. And then subtracting the first from the second, I will get alpha is m2 minus m1 divided by 2. So with those choices of m and alpha, that will guarantee that the slopes on either side of c will match up with the slopes of h. Now we have to match the value at c. Well, when I plug in c, I also want, plugging in c, that k should be equal to d. So what we have is two piecewise linear functions. They have the same value at c, and they have the same slopes on either side of c. So they have to be the same function.
And there you have x less than c, and you're mapping it to x less than or equal to c.
Oh, it doesn't matter because the values are going to match up at c anyway. Okay, so with these choices, what I will have then is that h of x is equal to m1 plus m2 over 2 times x minus c plus d plus m2 minus m1 over 2 times the absolute value of x minus c. So that piecewise linear function can be written as a combination of a linear piece and one of these absolute values.
Doesn't the function absolute value trying to do this? Doesn't that function, can't that function be like a W shape, or is it really confused?
I've only got one change of sign
Okay.
in the slope. Okay, so what I'm trying to do is match a function that looks like that and express it in terms of a linear
So it
piece.
stops at A and B, so it's not going to go back up since the absolute value. The absolute value part is different.
Right. Okay, so that's two changes of sign. So now suppose that it is true n changes of sign, or changes of slope, and consider a function h of x with n plus 1 changes of sign, changes of slope. So it goes up, say, and down, up, down, something like that. So let's mark in some points. That's x1, x2, x3. And that's xn. So each time we come to an x1, we have a change in slope for the piecewise linear function. Now what we can do here now write this as a function with n changes of sign, or slope, function with one change in slope. Now, pictorially, the way to do this so let us define h sub 1 of x to be whatever it was up to xn
should be xn plus 1. Because you change it every.
right, I had one slope to x1, 2 to x2, 3 to x3.
With changes in. So you have one change at each point.
Right, okay, so that should be xn, thank you, that should be xn plus 1. Right, so there will be n plus 1 changes in the slope. Okay, so I'll define it this way. It'll be the same picture as far as xn, or as far as xn plus 1, but instead of turning around and having another slope at xn plus 1, I will just continue that last straight line. So I'm now missing the change of slope that occurred at xn plus 1 in this picture. So this has n changes of slope. Now, of course, it's not the same function, but it is the same function as far as xn plus 1. So what should h2 be? It's going to be my original function h of x minus h1 of x. And what does that look like? Well, h1 and h are the same until I get to xn plus 1. So their difference is now 0 up to xn plus 1. The only difference will occur between xn plus 1 and b, where it's going to be the difference of two linear pieces. So that's another linear piece. So it'll do something like this. Maybe it goes the other way. Doesn't matter. So I simply alter my function to reduce the number of changes in slope, and then I adjust by adding back whatever change I made between x plus n plus 1 and b. It'd be a mess to write this down, but I think pictorially it's convincing. Okay. So, my hypothesis, my first function is a linear term, m1x plus d1, plus a combination of the absolute values of, well, the changes occur all the way up to xn. So sigma alpha sub k absolute value of x minus x sub k summed from 1 to n. So a linear piece plus a combination of these absolute values. But now we've already seen that if we have one change of sign, one change of slope, also h2 of x is covered by the case n equals 1, because it has one change of slope. Which means that h2 is some linear piece plus some multiple, so I'll call alpha n plus 1, times the absolute value of x minus x n plus 1. Add them together, so this implies that h of x, the two linear pieces sum to a linear piece, and then we have a sum k equals 1 to n plus 1, alpha k, absolute value x minus xk. So that's the inductive step, and therefore it is possible to write any piecewise linear continuous function as a sum of a linear term plus combinations of absolute value of x minus a certain point. So now, going back to where we started, remember we had piecewise linear continuous function that was within epsilon over 2 of our continuous function f. So now we write our g of x. We don't know how many terms we're going to need because we don't know how often it changes slope, but that's okay. It's a finite number of times. So g of x is equal to mx plus d plus the sum k equals, say, 1 to capital N alpha sub k, absolute value of x minus xk. So the previous result, by lemma 2.7, choose polynomials I'm going to index them by k and n. P sub nk of x so that the limit as n goes to infinity, the infinity norm of function x minus xk minus p sub nk of x is equal to 0. So for each term here, I'm picking a sequence of polynomials that converges to it uniformly. Well, since I have a finite linear combination, define Pn of x to be the linear term plus the sum k equals 1 to capital N alpha sub k times Pnk of x. The nice thing about polynomials is anytime you multiply them by scalars and then add them up, you're going to get another polynomial. So that's definitely a polynomial. And because individual terms converge to the right thing, we get that the infinity norm of g of x minus Pn of x goes to 0 as n goes to infinity. Because I only have a finite number of pieces to approximate, so I get arbitrarily close to each one. Okay, so choose n so large that the infinity norm of g of x minus Pn of x is less than epsilon over 2. Maybe I should call it n 0. And then the triangle inequality gives us that our original function f minus Pn0 of x, infinity, will be less than epsilon. So I can get as close as I like to my original continuous function using a polynomial. And it's just based on the fact that I can get as close as I like with a piecewise linear function. I should mention that this is a classical theorem. It has many proofs. So this is just one method of doing this. Okay, so that's the Stone-Weierstrass theorem on any closed interval. So we are going to generalize this now. To a setting where the closed interval a to b is replaced by an arbitrary compact metric space about if we really didn't use much about the closed interval AB, just that it was a closed bounded interval so that we could start off approximating by piecewise linear functions. Now, of course, the polynomials are not going to make sense anymore, so we need a replacement for the polynomials. Polynomials are replaced by certain algebras of continuous functions. So the main feature of the polynomials is that you can add together any two polynomials and get another one. You can scalar multiply a polynomial by a constant and get another polynomial. And you can also multiply together two polynomials and get another polynomial. So I have to say what we mean by an algebra. So a set A, since we're only discussing continuous functions, I'll keep it to continuous functions. The underlying space for this definition is basically irrelevant, but this is where we're going to use this. So a set A of continuous functions is said to be an algebra if the following conditions hold. The first condition is that if you take two elements in the set, f and g in A, implies that their sum is in A. Secondly, if f is in A and c is a real number, then c times f is in A.
Does C need to be a real number or in our metric space?
No, these are real valued functions.
Okay.
And so take a function, say double it. So these two together, I haven't quite finished, but these two together, in the language of linear algebra, says that A is a subspace of the continuous functions on X. And then the third condition makes it an algebra is that if you have any two functions in A, then we can multiply them together and get another function in A. So what that says is that the normal rules of arithmetic, adding and multiplying, will keep you within the set A. Okay, so let's look at some examples of algebras of functions. Well, we've already met one of them. So, first example, A is a set of polynomials on some closed interval AB. Secondly, A is a set of polynomials on AB so that the value at A is equal to 0. Now the reason that's an algebra, you just have to check. First of all, when you add, scalar multiply, and take the product, you get another polynomial. You just have to check that its value at A is always 0. So to see this, if 0. P of A times Q of A will be 0. And also C times D of A will be 0. So these are all polynomials, and all the operations of adding, scalar multiplying, and multiplying two of these polynomials together will preserve the condition of being 0 at the point A. So this is an example of an algebra of polynomials. It's strictly smaller than all polynomials because it doesn't have the constant function 1 in it. Example number 3. Let's let A be equal to the set of all things that look like this. Sum from 1 to n, alpha sub k, e to the kx, such that n is varying. Now, these exponentials are defined everywhere, so in particular, on any compact interval, this makes sense. So, is this an algebra? Well, yes. So the sum from 1 to n, alpha k e to the kx, plus the sum from 1 to m, beta sub k e to the kx, well, one of these numbers, m or n, is the smaller of the two. So let's say m is less than or equal to n. So when I add them together, this is the sum from 1 to m, alpha k plus beta k e to the kx, plus the sum from m plus 1 to n, alpha sub k e to the kx. So again, this has the same form, a linear combination of these exponentials. So that's in A. Also, too, when you multiply together two of these things, let me use a different index set here. Beta sub L e to the Lx. When you multiply these together, this is the sum alpha k beta L times e to the k plus L times x. So when you multiply together a linear combination of exponentials by another linear combination of exponentials, out comes a further linear combination of exponentials. So that says that when you multiply two things in A, you remain in A. So A is an algebra.
Professor, so with all these
spaces of functions were always coming out of the compact metric space. Is that compactness required to make it an algebra, or is that kind of?
No. All of this works on any subset of R. Right? I never use compactness here. But when we get to prove the generalization of the Weierstrass theorem, we will need compactness. However, I should say that there are some tricks for dealing with non-compact spaces as well that I'll show you, but we're not ready for that. So right now, we're just dealing with compact sets, underlying compact sets. Okay, and the last example for today. On negative pi pi, A is going to be the span of the functions cosine nx and sine nx for n greater than or equal to 0. Is everyone familiar with the term span? All finite linear combinations of these functions. You see that this is an algebra. Well, if you take two linear combinations of this and multiply it out, what terms are going to appear? You're going to have cosines, some sines. You're going to have some cosines times cosines, sines times sines, and cosines times sines. And as we have 1 minute left, I'll just indicate why this is true. So using the trig identity, cosine alpha plus beta, or plus or minus beta, is cosine alpha cosine beta minus plus sine alpha sine beta. We get that cosine alpha cosine beta is equal to cosine alpha plus beta plus cosine alpha minus beta divided by 2. So, for example, if we have a product cosine mx times cosine nx, plugging these in for alpha and beta, we'll get cosine m plus n x plus cosine m minus n x divided by 2. So a product of cosines can be written as a sum of two cosines. Same kind of thing with product of sine, cosine, and also sine, sine. So multiplying together things that are linear combinations of cosine and sine, using trig identities, you can express the product as another sum of sines and cosines. So this gives that A is an algebra. very important algebra. It's the underlying algebra for doing so-called Fourier series. The object of which is to take a function on minus pi pi and express it as a sum of sines and cosines. Okay, so Wednesday I will discuss the exercise. Let me just remind you the material for this test is chapters 0 and 1 from the notes. So nothing about approximating